This is where we were in our previous video. We completed this integration using direct line integration, right? And as promised, we're going to repeat the process, but this time we'll use Green's theorem. All right, let me just erase some of what were done earlier. Now let me erase some of these things too. All right, with Green's theorem. Now, of course, it satisfies the conditions for Green's theorem. It's a continuous function, it forms a closed loop, and it goes anti-clockwise, right? If you do it clockwise, you would have the sign negative. When you should have a negative, it will be positive. When it should have positive, it will be negative, right? Green's theorem. Now, the formula for Green's theorem is the integral along a curve around a closed loop of p dx minus q, no, plus q dy is equal to negative the double integral around the region would be the enclosed region, right? Around the region R of delta p by delta y, partial of p, that's the horizontal, partial of the horizontal component of the vector with respect to y, the vertical axis, minus partial of q, the vertical component with the horizontal axis, partial of x. All right, now here we have this minus sign. We did it before as it is, but if we get rid of the minus sign, sometimes you might forget that the minus sign was there. I accidentally write it without it. Let's switch this around. If we multiply everything by -1, the minus out here will become positive. The negative delta q by delta x will become positive, and the positive delta p by delta y will become negative. So let's just work with this as it is and see what happens. All right. Now, in the previous video, we did this by line integral. Let's use this now, Green's theorem, and see what happens. Now, you have to know your double integrals in order to do this. All right? Let's draw a bigger version of the double integral graph here. You have this, and oh no, let's redraw this part again. You have this and you have this. All right, now this is x squared, y equals x squared, and this is y equal x to the half, the square root of x. All right, now if you consider using horizontal strips, all right, let's start your surface, well, your double integral using this thing there, this element here, right? What you're going to have is a case here where you're integrating along the horizontal, right? You're integrating along the horizontal. because you want to use dx first. Remember, with these elements, just a quick review of the double integration with these elements, right? The width is delta x and the height is delta y, right? Now if you go across here, you are summing up, you're adding up from y equals x to the half, from y equals x to the half, from the left to the right, to y equals x squared. Alright? And the difference in measurement is along x, because you see x is the one getting longer here. Y isn't changing. You're not going up or down, you're going across. So you say delta x, right? Now you're integrating 1 delta x, even though you don't have to put the 1 there. Now, in order to fill up the region, you have to start stacking upwards. Alright? When you stack these things upwards, remember at first you went to the right, now you're adding up. When you start stacking them upwards, you don't have to say that you're going from x squared to x to the half, right? What you're doing is stacking from 0 to 1. Or if you say from x squared to x to the half, that would be a problem. The second integral that you perform, this one, must have numbers only to give you the answer. You see the from y equal x to the half to y equal x squared, that already takes care of the shape of the form, of the region. So you're adding from y equals, this is from y equals 0 to y equals 1. Alright? And then, as the limit of, when you start from what? From y equals 0 to y equals 1, what you're doing is adding up and changing y. So it's delta y, you have a change in y. Now the limit, as delta x tends to 0 and delta y tends to 0, then what you have is the integral from 0 to 1 of the integral from y equals 0 to y equal 1 of the integral from, I said, what did I say here? I had said y equal, for this one, this should be x equal, because we're going across, we need to transpose for x, right? My. So remember, if we go left to right, we're changing x to say from x equal. When you have y equal x squared here, it's the same as x equal. When you transpose for x, what you have? Square root of y, which is y to the half. So you're going from left to right. The right one is x equal y to the half. Alright. And the top one now, the left, I should say, y equal x to the half. If you square root them, if you y equal x to the half, and you want x equal, if you square, then x equal y squared, right? So you're going from y squared, x equal y squared, to x equal, I shouldn't bother erase what I had before, Let me make it remain. Y equal x to the half is the same as x equal y squared, right? You're going from x equal y to the half to x equal, you're going from x equal y squared, which is this curve, to x equal y to the half. So you're going from x equal y squared. So remember how we set up. It's going to take this is taking a bit long because we're not just looking at Green's theorem. We're reviewing double integrals because it's important that you review double integral, right? So yeah, in order to use Green's theorem, you have to know your double integral. So how we had set up the double integral? We start the elements from left to right along x dx. So we need to know what is x on the left and what is x on the right. X is y to the 2 on the left and x is y to the half on the right. So we're going from x is y to the 2 to x is y to the half. And after we stack from left to right, we need to go up in order to fill in the space. So we're going from y equals 0 to 1 and we're changing y. Alright? So the y to the half and the y square, these take care of the shape of what you have there. So as you have the limits tend to 0, and you have x equal y squared up to x equal y to the half of 1 delta x, no, d, it changes to d, dx dy. Alright? So that's what you have happened there. Now here when you have this and you integrate 1 with respect to x, you get x, and of course as you see here it is, oh hold on, it's not when you integrate, my gosh, you're integrating this. I forget about my thing there, it's not just double integration that I'm doing. I'm doing Green's theorem with that formula up here. Alright, so now that we remember our double integration, we need to set up Green's theorem now. Delta q by delta x, right? So, and you have delta p by delta y. Now this is in the form dx and dy. What is d? Well, what is p? P dx, p q dy. What is p? This is p, so p dx. So p is xy, right? So p equals xy. What is q? Q is 2x minus y. So q equals 2x minus y. Alright, so what is delta p by delta x? Delta p by delta x is just y. And what is delta q by delta y? Delta q by delta y is 2x. So you can put them in here now. The integral of delta q by delta x, delta q by delta x, delta p by delta y, delta q by delta x. My. Let's do this again. Delta q by delta x. When you differentiate q with respect to x, you get 2, right? So that's 2. Alright, so now we're back on track. Here we have delta q by delta x, which is 2. So what we're integrating here, oh, is this one. What we're integrating here is delta q by delta x, which is just 2 minus minus delta p by delta y, which is delta p by delta y that we're supposed to integrate. Oh boy, these mistakes, you know. Delta p by delta y. When you differentiate p with respect to y, you get x. Right. It's delta p by delta y, which is x. So we put x here. Alright. Now, it came to mind in the next video, I'm going to redo this, but I will assume that you are already very skillful at your double integration. So I won't bother to repeat the double integration part. It is going to be a review of this. So, let's get rid of the previous work we did. So here now, what we're going to have is, when you differentiate 2 with respect to x, you get 2x minus, when you differentiate x squared with respect to x, you get x squared over 2, and you're going from y squared to y to the half, and you're integrating from 0 to 1 of dy, because the dx part was just done a while ago. So x is 2y to the half now, so it's 2y to the half minus y to the half squared over 2, alright, minus the lower boundary is y squared, so it's 2y squared minus x squared, but x is y squared, so it's y squared over 2 minus, and then when you put in 0 for the other part, you get 0. So this is going to be the integral from 0 to 1 of all of this dy. So we have the integral from 0 to 1 of, alright, so now this is what? 2 square root of y minus square root of y squared, which is just y over 2. Right. So that would be y over 2 minus 2y squared minus y squared squared is y over 4. Y to the 4th over 2. Alright. So if we open the bracket now, let's say integral from 0 to 1 of, you're going to get 2 square root of y minus half y minus 2y squared plus half y to the 4th. Alright. Oh, dy. Is there any way we can simplify that? It doesn't seem so. Alright. So, that seems to be what we have to work with. Now, we're going to integrate and substitute the 1 and the 0. So, y to the half. Well, I shouldn't bother to write it square root of y now because we haven't differentiated yet. So let's rewrite it as y to the half. So this is 2 y to the half plus 1, which is 3 over 2 over 3 over 2 minus half y squared over 2 minus 2y to the 3 over 3 plus half y to the 5 over 5. Now we're going from 0 to 1. Alright. So you see that. Now, when we do this, 1, you put in 1 for y. 2 times 1 to the 3 over 2 is just 1. over 3 over 2. You have that. Minus y to the 1 becomes 1. I mean y squared becomes 1 squared. So it's a quarter. That part will become a quarter. Right? Minus this part is 1 to the 3, which is 1. So it is 2/3 plus y to the 5 is just 1, so it's going to be 1 over 2 by 5 is 1/10. Minus 0, so you don't have to worry about that part. So this is 2 divided by 2 by 3 over 2 is 2 times 2 over 3, which is 2 2's 4 over 3, minus a quarter, minus 3, minus 2/3 plus 1/10. Alright. And then we have this fraction to deal with. LCM. If we work this out as a fraction now, this would be, we could draw the line and find the LCM. Use that method. 4 3s 12. 3 LCM of 3 and 3 and 30. 32, 60. Is it 60? All of them can go into 60. Alright. So 3 into 60. 20, 24. 80. Minus 4 into 60, 15, 15, 1, 15. Minus 3 into 60, 20, 22, 40. Plus 10 into 60, 6, 616. Equal. So 80 minus 40 is 40. So it boils down to 40 minus 15 plus 6. Negative 15 plus 6 is what? It's going to be what? 9. So this part becomes 9. Well, what was it a while? Negative 15 plus 6. Negative 9. It becomes negative 9. So 40 minus 9 is 31. So it's 31 over 60. So, right, 31 over 60, the same, 31 over 60. Alright, good, good. Alright, so I'm going to redo the Green's theorem in the next video. But I'm going to assume that you already remember, you remember your double integral and so on and so forth. Alright? So let's do that in the next video. It's going to really be a summary of what was done here.